So, good afternoon, everyone. I'm Mukesh. I'm currently doing my MTech second year in microelectronics and VLSI design in IISc. In this presentation, I would like to give an overview regarding the questions which are going to be asked in many of the major companies. So starting with this presentation is mainly focused on the digital VLSI related questions. Because I have appeared for most of the digital VLSI companies, I would like to present you the questions which the companies have asked, and I would like to also give a quick overview regarding the topics which need to be covered for these interviews. So going to these technical rounds, generally there will be 2 technical rounds and followed by an HR. The first technical round will be an written test. Hello. Yeah, so there will be generally 2 technical rounds. First one will be a written test, and the topics for the written test are like most of them are from the gate, like the digital electronics and basic analog electronics and signals and systems. The questions will be of the gate level. Most of them are of that level or less than that. And but the problem with this written test is that the time duration will be the constraint here. So you need to cover the questions within the given time as specified by the company. And there will be some basic C questions, and aptitude will be common for almost all the written tests. And for basic C and aptitude, you can check Geeks for Geeks website. There they will be having some topic wise aptitude questions as well as the basic C questions. You can check the Geeks for Geeks website to practice these 2 topics. And there will be some Verilog syntax related questions, as well as there will be some questions on FIFO depth and setup time and hold time analysis, which is nothing but the static time analysis. So most of the written topics are of somewhat a gate level type, and there will be some good references for all the things. Like for digital electronics and these analog electronics and signal systems, you can see the gate papers or gate questions for practice. And for basic C and aptitude, Geeks for Geeks is better. For Verilog, if you are aware about the Verilog coding, then it will be fine. The questions will be to normal level, not very hard. And FIFO depth, I will mention some reference in the later slide. And setup and hold time analysis, this thing I will say some questions related to that. Okay, so coming to the interview may be of multiple rounds, like it may be 1 to 3 mostly. So the interview mainly focus on the projects mentioned by you in the resume or CV. And later there will be some basic digital questions, VLSI related questions, something like design related sequence detector circuits and timing diagram and hazards, and something related to the Verilog coding, where you need to code the given design what the interviewer has asked. And some of the companies like NVIDIA, Qualcomm, they focuses on these processor related questions, something related to the cache and pipelining. For this, you need to, in order to like answer these questions, you need to have strong basics of this our computer architecture related part. Okay. So coming to the questions, these are the few of the questions which some of the interviewers have asked me during the interview. So like coming to the combinational part in the digital design, we can expect the questions from these following topics like the gray code, logic, gates, marks. For example, here you can see that this is a very basic code, but just have get it for a good start. So the binary code for the gray code 1001 is 1101. So for this, there is no need to like write the complete equation and everything. There is a trick like for this conversion, the MSB bit will be the common in the binary part as well as the gray part. And in order to obtain the next MSB bit, you need to do the XOR operation of the obtained MSB bit of the binary input, binary output, and followed by the XOR operation of this second MSB of the gray code. So in this way, if you do the operation, you'll be getting this direct answer. The same thing holds for the reverse operation. Those things you can check. These are the basic, and something related to this XS3 and binary coded decimal. The codings, those are things you can check. Those are the very basic questions. Coming to this logic gates, this was the question which I have been asked in the Texas interview. So what they have asked is that how to implement some 3 input AND gate using NAND gates. For NAND gate and NOR gate, the associativity property doesn't hold. Like for a 3 input AND gate, using 2 input AND gate, you can directly implement it using the 2 input AND gates without any additional gate. Like for 3 input AND gate using 2 input AND gate, you can directly use 2 AND gates for this implementation. But coming to this implementation using NAND gate and NOR gate, after implementing the, like I will draw it once. So for NAND gate implementation, so these are the 3 inputs. The circuit which I have drawn is for the 3 input AND gate using the 2 input AND gate. So here the associativity property holds, and because of that, you are able to implement the things without any additional excess gates. But coming to the implementation using NAND gate, the associativity property doesn't hold. That is like A, B bar. Like I'm saying just the associative property. So if you remove this, ABC is not equal to A, B, C for NAND and NOR. So for this implementation, for 3 input AND gate implementation using NAND, you need to use additional gate. Here you need to use an inverter. An inverter, as you all know, it can be implemented again using the NAND gate. So after placing this inverter, you will be getting ABC bar, and in order to obtain ABC, you need to place other inverter. So what they have asked is that they asked the question in this way, like they asked to implement first 2 input NAND gate, later 3 input NAND gate, followed by 4. So after doing these all things, you will be generating some series. So after generating that series, you can directly answer what are the number of gates required for the n input implementation. This is the question which was asked in Texas. And similarly, uh, like you are all aware that NAND gate and NOR gate are universal gates. In the same way, MUX is also an universal block, and any function can be implemented using this MUX. Everyone will be aware of like how many MUX are required for the implementing 64 is to 1 using 2 is to 1 MUX. Like you will be doing the normal geometric progression type 64 by 2 plus 64 by 2 square plus so on 1. So we'll be getting some geometric progression series, and directly you'll be having some formula called 2 power n minus 1. Now this is for the inputs which are in the power of like 2 power n, which are in the format of 2 power n. But coming to the if the input, if it is like 66 is to 1 or something like that, like there which cannot be written as 2 power n format, then the minimum number of marks required will be different. Like the way you implement, it is going to differ. For example, if I say 3 is to 1 marks using 2 is to 1. So for this, the effective implementation is like if you assume 1 marks, so here directly we can implement the 3 is to 1 marks using 2 marks as itself. Whereas for the 4 is to 1, we'll be using 1 more marks. To implement 3 is to 1 marks from this 4 is to 1, here you can directly place the other input as ground. But the problem with this circuit is that here you are using 1 more additional marks, which is not required. So for the effective implementation of 3 is to 1 marks using 2 is to 1 marks, you can remove this circuit directly and you can connect the input to the C, and the select lines are given accordingly to select the proper input. So in the same way, like you can try for the some other implementation like 7 is to 1 or some other thing. So if you see again, there will be some series which can be observed, like the total number of marks required will be n minus 1. Even here you can see for 3 is to 1 implementation using 2 is to 1 marks, you require only 2 marks. The same thing holds for the any number of input marks, like it may be 1 is triple 1 is to 1 or anything. The total number of marks required is 1 to n minus 1. This thing can be verified from this geometric progression even. But you may be confused because of the number. This is something different which many of us have not seen even. Okay, so right. And those are the things related to the sequential. Now coming to the sequential part, most of the questions in the sequential are something related to the design. One small question I have left here. Here in the combinational, you can see this designing question, like number of ones, how to find the number of ones for a given n-bit number. This can be implemented using some combination circuit. I hope you can try this question and you can answer at the end of the session. Now coming to this sequential part, counters and shift registers, the questions will be like mostly related to these counters and shift registers, which are the key elements of the sequential circuits. And few of the questions are mentioned here. Oh, wait. Okay. So first question is like a D latch using 2 is to 1 marks. This thing is also easy to you. Like normal, the mux operation is, it is having few select lines. It is having a select line. For a 2 is to 1 marks, it is having a select line, and depending on the select line, it is going to select input 0 or input 1. So the basic operation of latch is also the same. In the latch operation, instead of the select signal, you need to place the clock. Now, depending on the clock, the first input will be the direct data. Like if you assume the clock is equal to 1, then this first input should be selected. And if clock is 0, then we need to store the input. So there is some feedback type here for the implementation of delatch using 2:1 marks. Okay. Now, like having said related to this, so this is the delatch implementation. So there are different, like if you invert these two inputs, it leads to the formation of positive latch as well as negative latch. Now, to generate flip-flop, you can use the similar concept of this and you can generate the flip-flop. Like the flip-flop is something like a combination of negative latch plus the positive latch. See, this is positive and this is negative. Yeah. Like you can verify this finally. Like a flip-flop can be generated using these two. Like if you are able to generate a positive latch and negative latch, then the flip-flop is automatically generated just by combining the things. Now, this frequency divider is a normal counter type, and there is nothing much special about it. Just I have placed it for to bring you attention related to these counters. In counters, I think you are aware of this preset and clear and how to use them. So this frequency divided by 6, it is a normal mod 6 up counter. So the implementation is the design is almost the design is the same as the mod 6 counter, and the output frequency which we are obtaining from the MSB bit is f by 6 here. Here I want to ask a question like the output which I am obtaining is of frequency f by 6. But what is the duty cycle? Is it 50% or anything different? And this you can answer at the last. Okay. Now, in order to implement a circuit of in order to implement a circuit of 2f frequency, this is not possible by a counter type because in the counter, the output which we are obtaining is like a frequency division type. So if you are giving a clock, f clock, the output which you are obtaining will be less than f clock. You cannot go greater than that. This can be implemented using some like this is the flip-flop. So the design will be something like it. Like you can verify it later even. So this is a normal counter. Here this is the T flip-flop and T is set to 1 and clock is given. So the output clock which I am obtaining will be f by 2 frequency. Now if I pass this 2 to the AND gate, what I obtain is that if I draw the waveform, so this is the f clock, the output waveform is f by 2 frequency. Now in order to obtain the 2f frequency, the required output should be in this format. So now using these two waveforms, how can you generate that? That is the main intention of this question. So it is like almost here, like if you draw the waveforms and if you see the output waveform, like you need to find some way in order to generate that. Like this can be generated even using the combinational part. And the combinational part, if you assume the clock and if you give some inverter, some series of inverters or buffers, and if you use some XOR gate type at the final, you can obtain this thing. So like if you give some f/4 delay to the clock frequency, and if you add it, then you will be getting the waveform of 2 frequency. Okay. This fourth question is also almost the same. Like you can design the circuit f/4 using the mod 4 counter, which is having 2 flip-flops. It can be the synchronous or asynchronous decision, something like that. So you'll be getting the final output as f/4 frequency. But here the question is that the duty cycle should be of 25% or 33%, something like that. Like the duty cycle should be like when considering this question, the output which I obtain will be like the duty cycle will be 50%. So the waveform will be on for 50% of the time. Now to obtain again 25% or some 33%, again you can use like the final output should be 25%. So this is the final. Okay. So you need to have output waveform on only for this 25% cycle. Like again in the last question what I have said, the same thing, like you draw the waveforms and you see if there is any other if there is some way to do this, something like okay, here the output frequency is f/4. Now in order to obtain this output waveform with 25% duty cycle, what should be done? That is the question. Like all the questions will be like in this way, like you need to have the output waveform and the input waveform, and you need to do something on the input side to obtain this output side. That is the main intention of any question. Okay, so now for this part, in order to obtain this 25% duty cycle, one thing what can be done is like here again you can shift the you can shift the f/4 waveform to some extent again to the front or back, and you can do some operation in order to get this. But the problem here is that like using this combinational circuits for the delay, this combination circuit can have variable delay depending on the input. Like if it is 1, the delay will be something different, and if it is 0, the delay will be something different. Like I'm saying, the delays will not be very close to each other. Like it will be close, but it will not be very close. Okay, so for this case you can use something like a negative edge detector. Again you can use a negative edge detector, and you can take the waveform of f/2 and you can generate a output from this, and you can do the XOR operations in order to obtain this 25% duty cycle. The same thing you can do for the 33% duty cycle. Like you can use some negative edge detectors like negative edge flip-flop, that is not nothing but, and you can generate the corresponding waveforms. Okay. Like again, there will be some questions on this Mealy and Moore. This Mealy and Moore, I guess it will be you will be having some basic knowledge about these state machines. Hmm. So, like I have given some reference for this, like I have found some pictures of Mealy and Moore in the online, and have placed something related to this. So it is something different detectors, both are, but I want to specify the difference between the two. Like the main difference between the two is that in the Mealy, you will have to like the output. the output 0 is going to depend on the present state as well as the input. In the but whereas for the more, the output is going to depend, the output 0 is going to depend only on the present state. Like if you are in S0, the output will be 0. In the similar way, if you are in the S3, the output will be 1. So here in the Moore machine, the outputs will be the dependent on the only the states, but whereas in the Mealy, the output will be dependent on the state as well as the input. So for this given for this given diagrams, you can find the sequence and you can answer at the end. In the same way, you can find the sequence for this Moore machine and the Mealy machine. And I hope you can try this 1001 sequence detector. And in some of the interviews, they may ask regarding the Verilog code of the state machine which you have drawn. So here you will be using, you need to use two always blocks, one for the sequential block and one for the combinational block. Here the sequential block is corresponding to this state, like the state is going to from S0 to S1, this transition occurs at every clock edge. So you need to specify all the things related to the state transitions in the sequential part. Whereas coming to this combinational part, this is related to the output. For example, in the Mealy, the output will be going to depend on the present state as well as the input. So you in this always, you can always at the rate, you can place the present state as well as the input, and you use some case, like depending on some if the transition is something, you can write some case statements here and you can code it accordingly. Like if you have any doubt related to it, I can answer it at the later. Like the coding is also easy. Like okay, so coming to next part. Next part is the logical effect. And as far as I can see, like there will be few questions from this, but it is better to understand the concept of this. Like you will this will be helpful in the sizing part, like sizing of transistors and those all things. You can understand from this part even. Okay, so some of the topics in this logical effort which I feel important are Elmore delay and this propagation rise fall time and the minimum delay. Okay, so few questions which I have picked from some book, Western Arrays. Okay, here and this figure shows the implementation of the 3-input NAND gate. Here, in order to find this rise and fall time for the 3-input NAND gate, like here the 2 and 3, those represent the size of the PMOS as well as NMOS. And this sizing, I think you are aware of them. Okay, like here the capacitance 9C is corresponding to the diffusion capacitance, and it is obtained like by addition of 3C and the 2 into 3. So it is 9C. And here it will be 6C in a normal way, but because of advancements in the layout, this will be like acting as a shade point. So the upper transistor and the lower transistor both are acting at the shade point, and hence it will be 3C instead of 6C. This is advancement in the layout. Like if you layout in some different fashion, you can like in some definite fashion, you will be getting this 3C. Or else if you layout in random way, you will be getting 6C. But 3C should be preferred because of the low parasitic. And in the same way, this is also 3. The input of the gate capacitance, you can add just 2 plus 3. Okay. Now rise time is related to the PMOS. Like the PMOS should switch on. Among these 3 PMOS, if any one of the PMOS is on, then the output will become 1. So this corresponds to the rise time. Like rise time is corresponding to the transition of the output from 20% of to the 80% of the VDD. Okay. Uh, okay. So this was the circuit for when only one. This is for the falling. Sorry. This is for the rising. Okay. Here, what was assumed is that only one transistor is on, and remaining transistors are off. So here we are considering the worst case. Worst case is the case where only one transistor is on. When you ask for the best case, it will be like when all the three transistors are on. Now, in order to compute the delay of this, for this worst case rise time, you need to use this Elmore's delay concept. So, according to that Elmore's delay, like the total propagation time will be the summation of RIS into CI. Here, CI is the node capacitance at all the node, and RIS will be the intersection of the resistance from source to output node and the source to the given node. Okay, if I will explain for this. Here, the source is VDD and the output node is Y. So in order to calculate the delay TPD, first we'll be considering this 9C capacitance, 9C into RIS. RIS here will be like only R, because from the source to node, like RIS will be like a intersection of the resistance from source to output and source to node. Here we are considering the node as Y, so it will be like RC, R. In the same way for the 3C part, 3C into here there is addition of resistance R by 3, but considering the formula, like we need to consider the intersection of source to out and source to node. So the intersection will be only the R. Again here we'll be getting the R in the similar way for the last case as well. 3CR. So this is the Elmore delay calculation. Okay. The same thing you can work out for this falling edge. Like in the same logical effect concept, there will be other concept for to find the minimum delay for the multiple part, like I have shown in the figure. So this calculation involves you to know the logical effort part, electrical effort, as well as the parasitic effort. So the normal, so the formula for this delay is D is equal to F plus P. Here F corresponds to the stage effort and F is given by G into H, where G is the logical effort and the H is the electrical effort and P is a parasitic delay. And I cannot explain the complete part here. You can see something related to these concepts, multiple part delay. The concept is, you can check it in online even. Okay. And there is other concept called power, and you can expect the questions from this, and most of them are like theoretical. It is not like the numerical part. Most of them like in the power will be having the static power and dynamic power concepts, and there is one formula for dynamic power, like it is given by alpha C F VDD square, where alpha is the activity factor. Activity factor, it corresponds to the number of transition in a given cycle. Like it is going to signify that part. And there are techniques to reduce this dynamic power as well as static power. These all things are like theoretical. You can check in some book. Okay. Like something which is very important is like the clock gating. Clock gating is mainly used to reduce the dynamic power consumption. And similarly, there is a concept called power gating, which is used to reduce the static power consumption. So these two are the remedies, like to decrease the dynamic power as well as static power. These two are required, and most of them, most of the part in the power is like theoretical, except this formula, and you can check it in some book. Okay. Like coming to the setup and hold questions, which is nothing but the static time analysis. I hope you are aware about this setup time for a flip-flop based design on the whole time. Like if there are two flip-flops and there is a combinational circuit in between, like both are connected with some clock. This is the combination circuit. Now, if there is some output coming from the first flip-flop, it needs to reach the second flip-flop like before the clock edge, and it should reach before the time TS. This is known as setup time. And the same thing, the output should be stable after the clock edge till the hold. Like at the edge of the clock, the input should be stable. The input should be stable before the edge till the setup time, and it should be also stable till the whole time. And I hope you are aware about these formulas and those all things. If you are not aware, you can ask me at the end. And the formula, the same formula using the clock skew, those all things. And what is this metastability? Like I have said you that the input should be stable in this window, setup and hold window. If by chance, if input is changed in this window, then there is a probability that output enter into some of the non-logical state. Like instead of 1 and 0, it may land in some between value. Like this is the some between, like there will be some tolerance for this logic 0 as well as logic high. If the value is in between, then the digital circuit cannot predict it is as 1 or 0. So this should be avoided. For the circuit to work properly, this should be avoided. Like the input should not change in the setup and hold window. And there are techniques to remove this setup and hold violations. Like few techniques, what I can say is, for the setup time, one of the basic thing what you can do is that you can increase the clock period. But if you increase the clock period, the performance of the system is decreased. So you can alternatively increase the performance of the combination circuit. Like you can decrease the delay of the combination circuit by using some like by using the large size gates, so that you can decrease the delay. You okay? And the same way for the whole, for whole violation to be removed, you can okay. Like for this whole violation, in order to be removed, like when a flip flop, the main place where this whole violation is occurs is for the shift registers. Okay, here for the shift registers, there is no combinational circuit part. Like the combinational circuit delay is 0, and hence what the expression for this whole will be like TTD should be greater than T whole. Okay, so this is the condition for the whole. Now generally for any circuit, this TPD will be greater than the T whole, so there will be no problem. But when skew enters, like if there is any skew between the two flip flops, then there will be a minus T skew. and there occurs a whole violation. Now this can be avoided again by inserting some buffers in the data path. You can insert some buffers so that this violation can. Okay. And there is also a concept called clock domain crossing. This, like when there are two clocks operating in two separate domains, like there is no relation between the two clocks, there is no phase relation and anything. When data in that one clock domain is sent to other clock domain, then there is a chance of this meta stability, like I have said before. So like the input may fall in the setup and hold window. Now, this if the input falls in this window, then the circuit output will be going into the metastability. Now, this should be avoided. This can be avoided using the synchronizers. Synchronizer is a two flip-flop design. It can be of any number of flip-flops even, but generally they will prefer these two flip-flops. With these two flip-flop, they will be providing some additional delay for the data, and hence the data will not come into that window. Like you can see the working of the synchronizers and those all things. Okay. But the problem with the synchronizer is that it is valid only for the single bit. If there are multiple bits, as I have said before, if I place some multiple synchronizers for the all the bits, but the problem is that all the bits may not reach at the same time because of the difference in the propagation delay of the flip-flops. So when there are multiple bits, one of the mechanism what industries use is the handshaking mechanism. Like you'll be sending some request and acknowledgement signals to know whether when to send the signal. Instead for transmitting this multiple bit, you'll use some single bit, and you see whether it is synchronized or not. The time it is synchronized, all the multiple bits are transferred. This is the handshaking mechanism. For the same multi-bit transfer, you can also use FIFO. You can study related to this FIFO. And the main questions what they ask is on the FIFO depth. Like what should be the size of the FIFO when the two clock cycles are, like I have given in the bottom one question. Like if the read frequency and write frequencies are given, like this is the FIFO. And there is write clock domain and read clock domain. Now, these two frequencies are in separate clock domain, and in order to synchronize them, we use these FIFO things. Like, okay. Now, this FIFO is essentially required when the write frequency is higher than the read. In the given question, the write frequency is lower and the read frequency is higher. So we don't require a FIFO. Like instead, we can use only a small resistor. One resistor is enough for this matching. Okay. Now for the like the FIFO works in the burst. Like you cannot transmit the data continuously. If you transmit the data continuously, then the FIFO size will become infinite, which is not practically possible. So the data comes in burst, like it comes in 100, something like that. Okay, like at a time 100 data will be coming, something like after 100 data will be getting some stop, again some 100 cycles, again some stop, and 100 data. Now for the same question, if the read and write frequency as swap, then you can use the formula to find the FIFO size. Like you can directly use. Okay. Now if the write frequency is 6 and read frequency is 4 and bus size is 100, then total time required for the FIFO, like total time required to write this 100 data for the frequency of 6, write frequency of 6 will be like 16.67. Now in this time, the total amount of data read by the read this clock domain, read clock domain, it will be like 66.65. Like you can multiply the frequency directly with this, so you'll be getting 66.68. So at this 66.67, the read clock domain has read almost 66. Now so the but the bus size is 100, so the required size will be like 100 minus 66. Okay, so this is some of the reference book. Like again, there some of the questions are very long. These are all the basics, and you can go through them. Like you can just check regarding them. What is the difference between a reg and wire? Wire is something like continuous assignment, and reg is used for the procedural assignment. And like how to instantiate a memory array or something like that, like which is having each of size 8 and 128 elements. And delatch using assign, these I have already said you, like how to implement the delatch using 2:1 marks. The same code which is used for 2:1 marks, you can use it for the delatch using assign. Okay, then this concept of blocking and non-blocking is important, and in many interviews they focus on this. Like the main difference between these two is that in the case of non-blocking, like these are the procedural assignments and are used in the always block. Now in this case of the non-blocking, all the statements in the always block are executed without blocking the flow, and all the things are updated at the end of the always block. That is the main difference. Like in the non-blocking, the flow is continuous, whereas blocking, it blocks. Like after one statement, you need to, after completion of execution of one statement, you need to go to the next one. But whereas in non-blocking, doesn't block the flow. So at a single time, all the statements in the always block are executed. Now the main difference for this, you can note in the shift register part. A shift register is generally implemented using non-blocking. And for this, for example, if you take 4-bit shift register, you can directly like assign the input of one flip-flop to the output. It is like just a connection from the input and output. Here with the non-blocking, you can directly write the statements in any order. But when you are implementing this 4-bit shift register using blocking, you need to follow some definite order in order to implement the shift register. If you follow in reverse order, then there is a probability that you will be getting a single register. So the ordering of the instructions is important when you implement the shift register using blocking. And the difference between this double equal and triple equal, the main difference is that this double equal is synthesizable and this is not synthesizable. But what this triple equal does is it checks for the x and z. Like if there are two numbers which is having some don't care and the high impedance, in order for the triple equal to be equal, the x and z need to be checked. Like in the two numbers, if there is any x, the other number should also have the x. But whereas for double equal, this x and z are considered as a don't care. And the same thing for this case and case x, case z. Like in the case, this 0, x and z are considered, but whereas in case x is considered as a don't care, and for case z, x and z are considered as don't care. Like these three are synthesizable, and after synthesis, all the three are the same almost. And you can see the difference between the function and task. Like the function is going to provide you a single output, whereas task is not going to provide a single output. And they from using the task, you can generate some multiple outputs. Like you can check the difference. And there is some like uh, uh, in the test bench you can use these things, like the delay in the Verilog can be uh, can be developed using this transport and the inertial delay. Like there are two types of delay in the Verilog: transport and inertial. This transport is implemented using optical fiber. This is using the RC concept. Now for this a given code, like it is like a test bench code, it is not synthesizable even. Okay, so here this asterisk is representing the delay. This is delay the assignment. Like this asterisk can be internal to the equal. This is called as the intra assignment delay. So the basic difference is that here if you place asterisk at the end, then the computation of A is equal to B plus C happens at 6. But whereas for this, like the B is captured at 0 itself, but it is assigned to the A after 6 nanoseconds. This corresponds to the non-blocking. Like for non-blocking, as I have said, the flow will be continuous. Like there is no need to stop. There is no need to wait for this delay for the next statement to be executed. But whereas for non-blocking, the delay will be significant for the next instruction. But for non-blocking, this is not significant. You can see some reference videos related to this. And some of the other concepts which which they may not ask in all the interviews, like something related to this ASIC design flow, they may ask regarding the flow, like synthesis, like first the Verilog coding, then the synthesis, then the placement and route, and the fabrication, like the complete flow. And something related to these single precision, double precision, floating point numbers. This I can see some YouTube lectures. This part is okay. Like this is also easy, like a static hazard detection. So if the hazard is static 0, then in the logic expression, you will be having some AND gate implementation between the original input and its complemented input. If it is static 1, then there will be a OR gate implementation of the input as well as complemented. Like for this case, here you can see that A and A bar are present. So if you assume that B and C are 1, then A plus A bar, you will be getting the output as A plus A bar. So this there is some static one hazard for the input A. Similarly, you can find some other hazards, like there is also an static 0 hazard for the B input. Now to eliminate these hazards in the K map, you need to map the all the adjacent elements. Like if there is two adjacent elements in the K map, then the mapping need to be done. Like even if it is not required, you need to do that mapping in order to avoid this static 0 and 1 hazards. And as I have said, there are some concepts related to this processor, something like speed up, cache size, and time, and related to the types of cache. Yeah, that's it. Yeah.
NPTEL interpreted. Yeah.
So let's ask the questions one by one. I will call the name. You will ask your question. It will be one by one. Not like it is not like hello. I will call the name. Ask your question. So first, um, Abhimanyu, do you have any questions? Abhimanyu. Okay, no. Amya, do you have any questions?
No, sir.
Okay. Arjun, do you have any questions?
No, sir.
Okay. Ashu Pandey, do you have any questions? Okay. Ashwani, do you have any questions? Bharat,
No, sir.
any questions? Okay. Goldie, do you have any questions? Hemanta, do you have any questions? Yeah. Goldie, tell.
Yes. So in Melee we have n states na, and for Moore it's n plus 1 na, but sir have mentioned n minus 1 and n.
Like 1 minute, I will share this. Like these two are independent state machines. Like though these two are not corresponding to any each other. Both are different.
Sir, these two are not for this 101. I mean 100.
Yes. These are not for 101. Like I have just picked it from the internet. Like just to show what is the melee and more. For the first case, it is some different detection, and for second case, it is different. Like for the first case, it is going to detect 101 sequence. For the second case, it is going to detect 101. It is going to detect 101. Yeah, both are same again.
Yes, okay, sir. And for that, for making 111:1 marks by with the use of 2:1 marks.
D-latch using 2:1 marks.
No, sir. Previous slide, sir. 111:1 marks.
Yes.
Yes, sir. This last question.
Yeah.
Yes.
You
Then
require
how many marks do we require, sir?
110.
110. Okay, sir.
Yeah.
Thank you.
Yeah. Okay. Fine.
Sir, it is 65 by 1, then 64, na?
65.
By 1, then how many
Yeah,
units, sir?
it is 64. Yeah, n minus 1 it is 64.
So
Okay.
for it is in generic form, we have to do that by two procedure. If it is in unavailable form, then we have to take n minus 1. That's it, sir.
Yeah, that's it. Yeah.
Yeah, thank
Yeah,
you.
you can check it for some other values even like 6:1 and 7:1. You can check and you can verify.
Okay, next. Bharat, do you have any questions? Bharat. Okay, next. Chitra, do you have any questions? Hemanta, do you have any questions? Kunal Agarwal, do you have any questions?
No, sir.
Lavesh, do you have any questions?
Yes, sir.
Yeah, tell.
So, what is the weightage of C or C++ in digital domains, and why are they asked?
Yeah, this
What
C
is the
question.
weightage in
Okay, yeah. Like it depends on the company. For example, Qualcomm, they provide some separate section for these C questions. Like they will be providing you 20 questions in separately without any connection. For Qualcomm, I have seen like it is separate. And for some other companies, there are questions not very much. Like the weightage will be like 10%, 5% around. Like total number of questions, 5% questions to 10% for other companies. But for Qualcomm, it will be there will be some separate section for this C. And aptitude, it is very important for almost all the interview, all the exams, I guess. Like there will be some separate sections for this aptitude even.
Okay, next. Madhavli. Do you have any questions? Madhav.
Yes, sir. Yes, sir.
Madhav, do you have any questions? No. Madhav, tell.
Sir, I am Ashwant.
Okay, tell.
Sir, you had covered. In which aspect you said, sir? RTL designing or which profile you said? All these things, sir.
It is for the digital.
It is for
No, that's what RTL
There
designing.
are two profiles. There are two profiles in Texas Instrument, analog and digital. So this is for the digital. Analog will be next week. Analog profile will be different faculty will be there and different candidate will tell about the analog.
Okay, sir. If you are going for digital, they will purely ask in digital.
Yes.
Yes. It is on campus.
Oh.
In the off campus, they ask system Verilog and UVM also. Right?
Oh, okay, sir. Okay, sir. Thank you.
Yeah. It is on campus also. This is to be noted.
Oh, okay, sir. Fine, sir.
Yeah. Then Madhav, Marlin Johnson, MS, Priyanshi, Sagar, any question? Okay. Sampath Kumar, any questions?
No, sir.
Sir, I have Sandesh. Yeah, Sagar, tell.
Actually, like still now, like 111:1 using 2:1 will be n-1. So what about 32:1 marks using 5:1, sir?
5:1.
Yes.
Hello. Okay. Yeah.
Yes, sir.
For those, like you can try designing using the 5:1 marks. You can check using the 5:1
Okay, like,
marks. Like the general formula, I'm not
okay,
aware.
okay, I'm not asking about the general formula, sir, but if they are simple like 6:1 using 4:1, I can do. I can try out that. If they
Yeah,
mention
those
like
things you
not
can
the
try out.
combination
Yeah.
of two. So like
Okay,
I
like
think I
basically
have
you
a
have
basic approach like a 6:2.
basically you have
6:1
to
using
try it on the
4:1.
pen and paper. It is not like it is in the mind. You have to try it on the pen and paper and check it whether it is right or not. It will take around 5 minutes to verify it.
These two questions are not direct questions. Like you need to,
Exactly.
they
Yeah, you have
started
to
from the basic.
exactly.
Okay, like how many select lines at least required, sir, for 6:1 using 4:1?
6:1 for 4:1. At least 6:1 you
Design
need
6:1
you
marks
require
using
3 select
4:1.
lines.
Okay.
Exactly my
3.
yeah. Thing is you have to try it on the pen and paper. You can't in 1 minute you can't say like 4 or 6 lines. Like you can't say you have to try it on pen and paper. Then it will take at least 5 minutes. I guess.
Like for
Okay.
like for 1 minute, yeah. 6:1 marks using 4:1 marks. You require
It will require
2 4:1 marks at least. Hello.
Yeah, you can continue.
Yeah, for 6:1 marks using a 4:1, you require at least 2 4:1 marks. First 4:1 marks will be having the 4 input lines, and this is connected to the first input of the second marks. Then there will be 2 input other lines. So overall 6 input, 6:1 marks. It is 2 4:1, and here the last output of the 4:1 marks will be 0.
Sir, but at the second marks, what you are saying, the first marks output is given as input to the second 4:1 marks, right?
Yeah. Yes, yes,
So,
yes.
but still, I can give 7 inputs if I'm designing like that, sir. So can you please check?
Yeah, I'm writing. So here there are 4 input lines, and this last output will not be used. Like as you have said that 6:1 marks using only 4:1. So this last output cannot be used. Like you cannot do anything regarding it.
Sir, in this, actually we need 3 selection lines now. So
Yes.
one can be used as a enable for
Okay,
2 by
okay.
taking 4 by n marks by taking 1 as a enable. So we are connecting 6 inputs, sir. For 2 we can make it ground for last 2. Can we do it? Can we do like that?
Like you are saying total 4 select lines now.
3 selection lines, sir.
Yeah.
For 6 inputs we have to take 3 selection lines, and I mean
Yes,
maximum 3. So by taking 2 muxes, 2 4 by 1 muxes, we given 6 inputs, sir. By taking 2 as a selection lines for 2 4 by 1 muxes, one must be taken as an enable input to both the 2 4 by 1 muxes. Can
Yeah,
we do
yeah.
like
One, yeah, one will be common. Yes, correct. Like one select line will
Next
be
is
common for both.
hello Sandesh. Do you have any queries? Sandesh?
No, sir. No.
Sharad? Shubham
No, sir.
Sharma?
No, sir.
Sid J, Siya Gupta,
No,
Sona
sir.
Das, Sumit,
No, sir.
Vikas Kumar, Yatin.
Yes, sir.
Yeah, tell.
Sir, do we need to study data structures also, or C is enough for written examination? Like
Very basic of data structure if needed.
Yeah.
In the test they will ask, but if you in the interview if they ask you did whether you know the data structure, you can simply get it is not in my touch from 2-3 years, so they will understand it.
okay, sir.
Mukesh, it is needed or not?
No, it is not needed. Like for some
Yeah,
specific
exactly.
companies,
Yeah. Exactly.
they may ask.
They may ask 2-3 questions, theory question in the test,
Yes,
basically.
yes. Yeah, 2-3
Right?
questions may be
Exactly.
expected.
Yeah. Hello, Vidya. Anyone have any questions now? We have covered everything.
Sir, I have it.
Hello, sir.
Yes, yes.
Yes. Ask. You tell me first.
Sir, in the first slide, you have mentioned that duty ratio 25%, 33%. Can you explain that, sir?
Okay, okay, yeah. This one.
Yes, question number 4.
It is, I have given the solution of this question in our course also, like in the digital electronics assignment. You have not gone through it, I guess. Yeah, you can add.
Here we'll be getting this f/2 signal, right?
Yes, sir.
So f/2 signal is this. Okay. Now, if you do just the AND operation between this and this, you can get the signal, right? 25% duty cycle. I think you have got it, right? Like just the AND operation between this f/2 and f/4.
Okay, sir. Yes, sir,
You can get this 25%.
Just a slight modification in the circuit is needed. It will be done using AND gate.
Is that okay?
Okay, sir. Okay.
Yeah, okay.
Sir, 33%?
33%, I think you need some other additional circuit. Like you need to have some like
I think
there should be something
XNOR
negative
gate or
edge.
inverter. XNOR gate is needed.
XNOR gate is
Inverter,
also
inverter or XNOR gate both will be useful.
Yeah, you need to have this negative edge flip-flop even, because this 33%, you can get some other extra percent from this negative edge clock. Like this will be available. Yeah, you can check it. This is a normal question itself.
Yeah, you
Okay,
just
sir,
have to try it on the pen and paper basically.
Yes.
Anyone have any questions now?
Yeah, one small thing. Yeah, anyone have this answer? Like any idea, rough idea of number of ones for a given number, how to find using combination circuit?
Sir, the meeting is about to end within 1 minute.
Okay, yeah. If anyone is having any doubt, then I can explain it, or else I can. Yeah, you can do
Anyone
it.
have any idea about it? You can explain it.
Yeah, you can do it using the full adder circuit. Hello. Yes. Yeah. So for this number of months for a given number, you can use a normal full adder. If the given number is 3-bit, if the given number is some 5-bit or some other thing, you can extend the things accordingly. I hope you have got some logic from this. Like you can extend accordingly for the 5-bit number. Hello, is that okay?
Yes, sir.
Yeah, okay. Any more questions?
Anyone have any more questions? So we are ending this meeting. Anyone have any questions? You can ask.
Yeah, you can ask anything.
Yeah. So let's close this meeting now. thank you so much, sir. Like,
Yeah,
was
thank
like
you everyone.
really
Thank
good
you.
session. Yeah, like,
Hello.
Sir, hello.
Yeah, yes.
Sir, portion of computer architecture, sir.
Portion of computer architecture. These things you can see in some.
in our course structure also. So you can go through our syllabus also. What are the things needed? We have topic wise. We have tell like what is the course structure also. So you can just go through it also. Some topics are important like analog EDC, computer architecture, microprocessor, C++. Some topics are important. Whole subject is not important. Even
Yes,
from
yes.
the EDC, they ask short channel effect, long channel effect in the digital profile also sometimes, right?
Yeah.
So these topics are important. There are like 30 topics in 20 to 30 topics like in computer architecture which are important, not much. Yeah, so we are ending this meeting. Thank you so much to everyone and thank you, sir. Like it was a really good session.
Yeah, thank you
Thank you so
everyone.
much.
Thank you, sir. Thank you, everyone.
Thank you.